this lecture on basic system models, thermal systems, and of course, this a sub module for the course on modeling and simulation of dynamic systems. Okay. So, in this module we will be discussing about the basic building blocks required to model a thermal system. Okay. And initially we will be looking at those building blocks, and then we will take up those building blocks expressions in order to model a thermal system. So, in thermal system there are only two basic building blocks which are used to model the thermal system, and these building blocks are the resistance and the capacitance. Okay. So, let us see one by one. First we take up the thermal resistance building block. Now, you see that there is a net heat flow between 2 points if there is a temperature difference between them, and a relationship for thermal resistance can be defined similar to that of the electrical resistance. Okay. That is, Q is equal to T1 minus T2 upon R. Okay, where the T1 minus T2, these are basically the temperature difference, and R is your thermal resistance, and Q is the rate of heat flow. So, you can see that this expression is very similar to I is equal to V by R. So, what does this means? This means that the temperature difference in the thermal system corresponds to the voltage drop in the electrical system, and rate of heat flow in the thermal system corresponds to the current in the electrical system. Okay. And of course, here we have the thermal resistance, and here we have the electrical resistance. Now, the value of thermal resistance depends on the mode of heat transfer, that is, whether the heat transfer is taking place through convection or through conduction. Okay. Now, for unidirectional conduction through a solid, we know that Q is equal to AK T1 minus T2 upon L. Okay. So, where here you know A is the cross sectional area of material through which heat is being conducted, and K is the thermal conductivity of the material, and L is the length of the material between the points. Thus, if I try to write this expression in the form of the definition which we have given for the thermal resistance, this L upon AK basically belongs to the thermal resistance. So, you can say that the thermal resistance for the conduction is L upon AK. Okay. That is what I was telling you, that our general expression is Q is equal to T1 minus T2 upon R. Okay. And for conduction, this Q is equal to your AK and T1 minus T2 upon L, or this I can write as T1 minus T2 divided by L upon AK. So, this term corresponds to this thermal resistance. Alright. So, this is for the conduction. For convection heat transfer, that is liquid and gases, heat transfer through liquid and gases, the relationship is Q is equal to HA T1 minus T2. So, this is for conduction, and for convection Q is equal to HA T1 minus T2, or I can write this as T1 minus T2 divided by 1 by HA. So, this basically corresponds to your the thermal resistance. Okay. So, this way here we define this the thermal resistance for case of the convection. Okay. Now, here A is what? It is the surface area across which there is a temperature difference, and H is the coefficient of heat transfer. And so, from here I define R is equal to 1 by HA. Okay. Next building block is the thermal capacitance. Now, the thermal capacitance is a measure of store of internal energy in a system. Okay. So, if input and output flow rate of heat are say Q1 and Q2, then the rate of change of internal energy is equal to Q1 minus Q2. And what is this? This is basically equal to MC into rate of change of temperature. Okay. Where what is M? M is the mass and C is the specific heat capacity. Okay. So, I can write this as MC into dt by dt, and this dt by dt is the rate of change of temperature. Okay. So, this way we define this, and this Q1 minus Q2 is equal to MC dt by dt. I can give a single notation for this M into C, which we call it as the thermal capacitance. So, this is what we get, Q1 minus Q2 is equal to C dt by dt. Okay. And if I compare it with the electrical system, then my V is equal to 1 by C. Basically, this is the Q term, that is the charge across the capacitor plate, and when expressed in terms of current, it is integral I dt. So, from here I can write I is equal to C dV by dt. Now, if I compare these two expression that is of electrical system and that of the thermal system, then you can see that I corresponds to Q1 minus Q2 here and V corresponds to T here. Okay. And then we that way we can define the thermal capacitance using this equation. Now, using these two expressions for the thermal capacitance and thermal resistance, we can model any thermal system. Okay. So, let us see. First of all, we take up an example of a thermometer. Alright. So, suppose this is a container, and in this container say there is a liquid whose temperature is TL. Okay. I insert a thermometer in this liquid. Okay. So, what happened? There is a heat transfer from liquid to the thermometer, and because of that, say the temperature or the mercury level indicates a temperature T there by the thermometer. Okay. So, here as I said, the liquid at temperature TL and thermometer has been inserted and it reaches a temperature T, which is indicated by the height of the mercury column in the thermometer. Now, if the thermal resistance is R, then the heat flow from liquid to the thermometer. Okay. This can be given by Q is equal to TL minus T by R. Okay. So, this equation we got from the definition of the thermal resistance. Okay. So, here the R is the thermal resistance, Q is the heat flow from the liquid to thermometer, and TL minus T is the temperature drop. Now, after defining the thermal resistance, we can define the thermal capacitance, and then we combine those both of these expressions, that is the expression of thermal capacitance and the thermal resistance. Okay. So, the thermal capacitance of the thermometer is given by Q1 minus Q2 is equal to C dt by dt. Okay. We have just seen from the definition of this thermal capacitance building block. Now, here Q2 is 0 since heat flow is only from liquid to the thermometer. Okay. So, I take this Q2 is equal to 0. So, what I have Q1, let me just write it as Q here is equal to C dt by dt. Okay. And this Q I can replace from the definition of the thermal resistance, that is TL minus T by R. Okay. So, if I do that, this is what I get, TL minus T by R is equal to C dt by dt. Okay. Or I can write this expression further as RC dt by dt plus T is equal to TL. So, here you see what is our input? The input here is the liquid temperature TL, okay, and what is my output? Output is the temperature of the thermometer or temperature displayed by the thermometer. Okay. So, this expression is basically the first order differential equation, and this tells us basically that how the temperature of the thermometer or temperature indicated by the thermometer is going to change with time, okay, for the given input TL, for the given input TL here. Okay. Now, let us take another example. This is example of say heating of a room. Okay. So, suppose this is my boundary of the room, alright, and here there is a heating coil. Okay. This symbol basically indicates the coil, a heating coil. Okay. So, we have the heating coil, and heating coil actually gives a heat flow of Q1. Because of the heating coil, say there is heat flow of Q1, okay, and because of that there is a room temperature of say T, fine, okay, and the thermal capacitance here is say C. Now, beyond the wall, okay, or say from this room to the other side through the wall there is heat transfer Q2, okay, and say the surrounding temperature is T0. Okay. Then as I said, we can write the expressions here, alright. Then as I said, here we are talking about heating by a electric fire and heat input by the fire Q1 and heat loss from the room is Q2 at the room uniform temperature of the room T and the surrounding temperature T0. So, let us say we assume that there is no heat storage by the walls of the room, that is the walls of room do not store any heat, then the question is that how the room temperature will change with time. Okay. So, let the thermal capacity of the room be C, then we can define Q1 minus Q2 is equal to C dt by dt. Okay. Here Q2, what will be Q2 basically? T minus T0 by R. So, temperature this side is T, this side is T0. So, T minus T0 by R, this is what is going to be the Q2, where R is the wall thermal resistance. So, what essentially I am doing is I am defining the thermal capacity of the room and I am defining the wall thermal resistance, and now I can combine both of these equations. Okay. So, if I combine, that is if I substitute for Q2 here, this is what I get. Okay. So, if I put Q2 T minus T0 by R, I cross multiply by R. So, I get RC dt by dt plus T is equal to RQ1 plus T0. Now, here you see what are the input here? The input is my Q1, okay, and here again this expression is a first order differential equation, and you can see that this expression tells us how the temperature of room is going to change with time. Okay. So, this way for a given Q1 or given input of Q1, we can find out how the temperature of the room is going to change with time. Okay. So, next let us take a little further complicated system, that is thermal system involving two compartments. Okay. So, suppose this is my compartment 1 and this is my compartment 2. Now, here say there is a heating coil, okay, which is giving a heat of Q to the room. Okay. The room temperature is say T1, its capacitance is C, and there is a Q1 heat transfer taking place between room and surrounding, and this surrounding is at temperature T3. Okay. Say there is adjacent room or say compartment Q2, compartment 2. Now, the temperature of the compartment 2 is say T2. So, you are going to have a heat transfer from compartment 1 to compartment 2, say this is Q2, as well as you are going to have heat transfer between compartment 2 and surrounding, and say this is Q3. Okay. And we assume that the thermal capacitance of both the compartments are say C. Then I can write the expression for first compartment, alright, and remember we are going to use the two basic building blocks here for the thermal system, and these are the thermal resistance and the thermal capacitance. Okay. So, let us go for the first building block. So, thermal capacitance. So, what is my net heat in? Okay. So, Q is my input and Q1 and Q2 are output from the first compartment. So, my net heat influx is basically Q minus Q1 plus Q2, and this is equal to C dT1 by dt, where T1 is the first room temperature. Is that okay? Fine. Now, what is Q1? I can write this Q1 as T1 minus T3 by R. Okay, where this R is the thermal resistance of the wall and T1 minus T3 is the temperature of the compartment 1 and the surrounding. So, this is how my Q1 is going to be. So, this Q1 is T1 minus T3 by R. Okay. Likewise, I can write values for this Q2. This Q2 is T1 minus T2 by R. Of course, here I am assuming that the thermal resistance is same for the wall, okay, and it is same at all sides, say here, fine, okay, and I am not assuming that any heat transfer taking place from this to this one and similarly from here to here. Now, what we can do is that, remember our Q is the input, okay, and the output my is T1, that is I want to know how the room temperature T1 varies with time. Okay. So, I substitute for Q1 and Q2 here in this equation, and this is what I get, Q minus T1 minus T3 by R plus T1 minus T2 by R is equal to C dT1 by dt. Or as I said, my interest is to know about dT1 by dt. So, I can write this as RC dT1 by dt is equal to RQ minus 2 T1 plus T2 plus 2 3. Here this T1 plus T1, these two terms will be getting added up. So, they will be giving you 2 T1 term, and of course, we have a T2 and T3 term. So, this way we get it. So, this expression basically tells you that how the temperature of the first compartment is going to change with time. Okay. Next, we can look at how the temperature of the second compartment is going to change with time. Okay. So, let us see how do we do that. So, here this is my second compartment, fine. Now, in this compartment what is the net heat flow? So, you see that in this compartment the heat in is Q2 and heat out is Q3. Okay. So, this is Q2 and this is Q3. So, the net heat influx is basically Q2 minus Q3, okay, and this Q2 minus Q3 is equal to C dT2 by dt. So, this is expression basically which comes from the thermal capacitance, okay, and I can write the expression for Q3 here, okay, by defining the thermal resistance of the wall. So, this Q3 is T2 minus T3 divided by R, okay, and I can substitute this Q3 value from this expression into this one. So, what I have is Q2 minus T2 minus T3 by R is equal to C dt2 by dt, and this Q2 value I get from the first expression for the first compartment here, this one, okay. So, this is my Q2, that is T1 minus T2 by R. So, this is how that is we define the thermal resistance for this wall, okay. So, that I am putting here Q2 is equal to T1 minus T2 by R, and this is my Q3, that is T2 minus T3 by R is equal to C dt2 by dt, okay, and this way I can find out RC dt2 by dt is equal to, we have the T1 term here and then we have minus 2 T2 term and then we have a T3 term, okay. So, this expression actually tells you that how the temperature of the second compartment is going to change with time, okay. Fine, thank you.